It never begins with a clear signal. There is no siren that tells millions of people to move at once. Instead, it starts with a pattern shift. Traffic density increases by 12% over baseline, fuel stations begin reporting localized shortages, and logistics networks quietly reprioritize deliveries away from urban centers. Within hours, the system enters a state emergency planners refer to as asymmetric evacuation pressure. And this is where the real danger forms, not in the collapse itself, but in where people choose to go when they believe escape equals safety. Because most people do not evacuate strategically. They evacuate emotionally. They follow highways, headlines, and assumptions. And those assumptions concentrate risk into predictable corridors, interstates, coastal routes, and suburban expansions, turning them into bottlenecks of exposure. But while those zones begin to overload and destabilize, a small number of locations behave very differently. They do not attract movement. They resist it. And under stress conditions, they transform into something rare in a failing system. Stable, defensible, resource-sustaining environments that function more like fortresses than refuges. The first of these locations does not look like a fortress at all. In fact, under normal conditions, it appears almost invisible. Mid-sized industrial zones positioned just outside major metropolitan areas, often dismissed as logistical dead space. These are areas built around warehousing, light manufacturing, and freight handling, typically located along secondary transport arteries rather than primary evacuation routes. When a population begins to move outward from a city, these zones are bypassed. The flow of people overshoots them, heading toward perceived safety in rural or suburban regions. But this is the first critical misunderstanding. Distance from a city does not equal survivability. The hidden science lies in infrastructure density versus population density. Industrial zones are engineered to support high throughput, electricity, water, fuel access, and structural capacity, without requiring large residential populations. That means when evacuation occurs, these areas retain disproportionate access to utilities relative to the number of people present. Backup generators are common. Water systems are overbuilt. Storage capacity is high. And most importantly, access roads are designed for trucks, not mass civilian traffic, making them less prone to gridlock. Evidence from disaster response models and real-world events consistently shows that secondary infrastructure corridors maintain functionality longer than primary evacuation routes. During large-scale disruptions, whether from natural disasters or system failures, freight networks degrade more slowly than civilian mobility networks. This creates pockets of operational continuity in places not designed for habitation, but perfectly capable of sustaining it. The survival implication is counterintuitive. While millions move outward seeking space, the most stable zones are often those with controlled access, existing infrastructure, and minimal population pressure. Industrial perimeters can be secured more easily. Movement can be monitored. Resources are centralized. And because these areas are not perceived as destinations, they avoid the exponential strain that collapses other locations. But this stability does not last indefinitely. As supply chains continue to degrade and information spreads, these zones risk discovery. And once discovered, they face a different kind of threat, not overload but targeted influx. This is where the second location diverges sharply in structure and function. High elevation settlements, particularly those situated along limited access mountain corridors, behave in an entirely different way under evacuation conditions. At first glance, elevation seems like a disadvantage. Reduced oxygen levels, harsher climates, and limited agricultural potential suggest vulnerability. But in crisis modeling, elevation introduces a critical variable: friction. Friction in this context refers to the difficulty of movement. Steep gradients, narrow roads, and weather variability create natural barriers that slow or prevent mass migration. When large populations attempt to evacuate, they prioritize routes of least resistance: flat terrain, wide highways, predictable conditions. Mountain access points become self-filtering systems, allowing only a fraction of movement to penetrate. The misunderstanding here is that accessibility equals safety. In reality, accessibility invites saturation. Locations that are easy to reach become impossible to sustain once population exceeds resource capacity. High-elevation settlements, by contrast, limit access not by policy, but by physics. The hidden science involves energy expenditure and vehicle performance. As altitude increases, engine efficiency decreases due to lower oxygen density. Fuel consumption rises. Mechanical strain increases. This reduces the range and reliability of vehicles attempting to reach these areas, effectively creating a passive defensive perimeter. At the same time, lower temperatures reduce bacterial growth rates, extending the viability of stored food and limiting certain disease vectors. Historical and contemporary data from isolated highland communities show remarkable resilience under supply disruption. These areas often maintain independent water sources through snowmelt or gravity-fed systems. Their lower population densities reduce immediate resource competition, and their geographic isolation delays the arrival of external threats. But elevation introduces its own risks. Medical emergencies become more difficult to manage. Agriculture is limited by shorter growing seasons. And long-term isolation can create sustainability challenges if resupply is not re-established. This creates a temporal window of advantage, strong initial stability that must transition into long-term adaptation. As evacuation patterns evolve, the pressure shifts again. Lowland and suburban zones begin to destabilize under resource depletion, while isolated areas maintain relative order. But a third type of location begins to emerge as uniquely resilient, not because of isolation but because of structural design. Large institutional complexes, universities, research campuses, and certain corporate headquarters are often overlooked in survival planning. Yet these environments are engineered for semi-autonomous operation. They contain redundant power systems, water treatment capabilities, food service infrastructure, and in many cases on-site medical facilities. The danger, however, is perception. These locations are seen as public or accessible, which under normal conditions is true. But during system stress, access points can be controlled, perimeters can be secured, and internal resources can be rationed with a level of organization that most residential areas cannot achieve. The misunderstanding is that these complexes are too visible to be safe. In reality, their scale and design allow for internal regulation that smaller communities lack. They are not dependent on immediate external supply if properly managed, and their infrastructure is built to handle thousands of occupants under controlled conditions. The hidden science lies in systems redundancy. Critical facilities are designed with fail-safes, backup generators, multiple water sources, layered communication systems. This redundancy extends operational lifespan far beyond typical residential infrastructure. Additionally, the presence of technical expertise within these environments, engineers, medical personnel, logistics coordinators, creates a knowledge advantage that directly translates into survival capability. Evidence from emergency preparedness studies shows that institutions with pre-existing crisis management frameworks outperform ad hoc community responses. They can implement rationing, maintain sanitation standards, and coordinate internal security with far greater efficiency. But this advantage is conditional. It depends on rapid transition from open access to controlled access. Delays in this transition can lead to overcrowding, resource depletion, and internal instability. Timing becomes critical. And as more people recognize the stability of such locations, they risk becoming focal points of convergence. This escalation leads to a broader realization. The safest locations are not defined by remoteness alone, but by the balance between accessibility, infrastructure, and controllability. Too accessible and they collapse under pressure. Too isolated and they struggle to sustain long-term survival. And as the system continues to strain, a fourth category begins to reveal itself. One that combines elements of both isolation and infrastructure, but operates under an entirely different principle of resilience.